All right, welcome back, guys. We're getting close to a solution here. What we're going to do in this video is we're going to solve for this value and this value, this JT WJW and this JWWJWWWWW. And the way we're going to do that is we're going to use our terminal condition. This JW big T is equal to U bar of W. If we know nothing more than just what's written, not this utility function, just these two equations, this is not a solvable system of equations analytically. We could do like a computer simulation or something and find an answer. But by making an assumption about the utility function, then you will be able to find an answer, because we'll be able to compute derivatives of this JWT. So we just need to pick a convenient utility function that seems like we can defend choosing this one. Anything will do, but we're going to choose the CRRA utility function. You could choose a Cobb-Douglas utility function, a CES utility function, a quadratic utility function. This is really an arbitrary choice at this point. I'm choosing this one because this is the one we chose in class. But, you know, that's maybe something you can think about. I could certainly imagine a test question where he asks you to do a similar exercise, but with a different utility function. The steps would be exactly the same. You would just get different results. We'll assume that our gamma falls in this top case, so we won't look at the log investor right now. We'll look at this top one. So given that, we have from our terminal condition that JW big T is now equal to W1 minus gamma minus 1 over 1 minus gamma, which is great, but we want to know what is the function JW little t. And to do that, we have to use a discount factor, and we have to roll back the wealth. So if we imagine that this first function here is the utility, this W, and this utility is the final utility, the utility at time t, time big T, it stands to reason that we could just apply some discount factor, and we'll call it eta, t minus t, to that wealth with the exact same other functional form, and that will give us the utility at any time t by just starting at the end and then rolling it backwards using this discount factor. And so now what we can actually do is we have a form of this JWT function that we can take derivatives of. And so we can start to find values for this JT, this JWT, and this JWWW and all of this. So let's start with just taking these derivatives, and then we can compute the fractions. So JT, which is going to be the derivative of this with respect to t, we're going to get a minus eta out of the chain rule here. E to the eta t minus t, W1 minus gamma, divided by 1 minus gamma, and everything else is the same. So here's our JT. Now we can take our JW. So JW, we're going to get a 1 minus gamma down, W to the minus gamma. This discount factor just comes along for the ride. T minus T divided by 1 minus gamma, and that minus 1 again just goes away. Great. So then we can now compute the second derivative with respect to W, because we also want to know JWW. So now here we're going to bring down another minus gamma, 1 minus gamma, W to the minus gamma minus 1 to the n t minus t over 1 minus gamma. Great, so we wanted to know two fractions. We wanted to know what is, let's scroll up and check, what is JT over WJW. So let's start there. What is JT over WJW? So let's just transcribe. JT is going to be minus eta, e to the eta t minus t, W1 minus gamma over 1 minus gamma. For the WJW, I'm going to write this as the multiplication of the inverse. So we'll have a 1 minus gamma on top. And then we're going to have W 1 minus gamma, W minus gamma, e to the eta t minus t. So right away we see that the discount factors cancel. That's nice. And we can also see that this 1 minus gamma cancels here and here. So we're left with minus eta W 1 minus gamma over W times W minus gamma 1 minus gamma. And this is just equal to W to the 1 minus gamma, so this and this cancels. So we are left with, this is equal to minus eta over 1 minus gamma. And that is equal to JT over WJW, given that our utility function has been chosen as the CRA, and given that this gamma does not equal 1. Great, so our other fraction we're interested in, moving up, is JW over WJWW. JW over WJWW. And that's going to be equal to, I take a deep breath before I start saying all these W's, minus gamma e to the eta t minus t divided by 1 minus gamma, and again times the inverse, so we're going to have 1 minus gamma times minus gamma 1 minus gamma w to the minus gamma minus 1 e to the eta t minus t w. So again, we see, of course, these cancel and the discount factors cancel. So we have 1 minus gamma w to the minus gamma divided by minus gamma 1 minus gamma w to the minus gamma minus 1 w. And once again, this worked out nicely. Minus gamma is equal to minus gamma minus 1 w. So this cancels with this, and this cancels with this, and this is equal to minus 1 over gamma. So you can see one nice feature of this CRA function is that actually the answer, this derivative, works out exactly the same as we had been defining this 1 over gamma term in the past. My assumption is that the early researchers on this, Merton and Black and Scholes, they just used the CRA function. So now when we see this JW over WJWW in our drift term calculation, we just say, oh, let's define that as 1 minus gamma. But here is really where it comes from. So we've got this value here and this value here, and we can actually just plug them back into our equation to find our optimal wealth. And we will do this in the next video because I'm out of room. So I'll see you there.